Hello everyone, this is Emily and Jeffrey from Team Super Firewall Unicorns, here to discuss how we designed and implemented our question generation and answering system. Our goal was to create a program that reads a Wikipedia article and understands it well enough to generate and answer questions. When we started this task, we imagined a system that would extract factoids from the text into a database. Both our questioning and answering systems would draw from this pool of knowledge to complete their tasks. However, we realized that this sets a hard limit on the types of questions we'll be able to generate. So instead, we directly manipulate the syntactic structure of the article to form questions. However, this assumes that the article is long enough to have the syntactic structures we like. Now, in order to answer questions, we perform fuzzy matching between the sentences in the article and the questions. This allows us to identify potential answers from the best matched sentences. This method is based off the assumption that, since questions are fluent and reasonable, the questions will contain a lot of semantic words. Here's how we implemented the system. We start by pre-processing the article. We split the article into sentences and then take each sentence and tokenize and parse it with the Berkeley parser. This gives us a parse tree and a probability for each sentence. In addition, we run the Lancaster stemmer over all the words and then create sentence vectors based on the count of each word. We treat each sentence in the article as a document to compute the inverse document frequency of each of the stemmed words. This assigns a higher weight to more significant and rare words. What we'll do with this will become clearer when we discuss the answering module. But first, we'll explain how the asking module works. After pre-processing, we have a collection of sentence parse trees. We remove trees that are no good for question generation, such as if they're too short, if they have no verbs, or if they have too many pronouns. Co-reference resolution doesn't work very well, and so by avoiding questions with pronouns, we avoid generating awkward questions, even if those questions could contain important factoids. Now, whenever we have a sentence made up of a noun phrase and a verb phrase, it's like an informal factoid. The subject noun phrase satisfies the predicate verb phrase. But wait, there's more. There are more patterns in syntax that can express semantic relationships. For example, if we find two noun phrases separated by a comma, those noun phrases are usually describing the same thing in two different ways. So we can transform this subtree into the sentence, noun phrase 1 is noun phrase 2, and add it to our pool of sentences. We have a bunch of hard-coded pattern matching rules like this that give us a lot of new sentences to generate questions from. There are two major types of questions that we can generate: yes-no questions or identification questions. Who, what, where, when, which, why, and how. To generate a yes question from a sentence, we 1. Augment the central verb with a modal verb, 2. Move the modal verb from the middle of the sentence to the front, and 3. Add a question mark. To generate a no question, we take a yes question and corrupt a random word in hopes of changing the meaning of the question. We can mutate common nouns by finding their hypernym in WordNet and then finding a hyponym of that. We corrupt proper nouns by swapping them with another, and we literally fudge numbers by multiplying them with random factors. Generating WH questions can be trickier. We run a supersense tagger over our source sentences. It's like a name entity tagger, except words are tagged with their WordNet class. This way, we can identify people, organizations, locations, durations, and objects, and replace them with the corresponding question word: who, what, where, and when. We usually only replace an entity if it's the first word in the sentence, which maintains the grammaticality of the sentence. After we've generated a large pool of questions, we score the questions with three main goals. Is the question reasonable, fluent, and intelligent? To make sure questions are reasonable, we penalize questions that are too short or too long, or have negation words in them, since those are usually confusing. We give bonuses to prepositional phrases, since those add context to questions. Next, we score the questions based on how fluent they are. To check for grammatical correctness, we use a question tree bank to train a grammar of English questions for the Berkeley parser, as if we were working with a foreign language questionese. This allows us to retrieve the probability that a string is an English question, which is more useful than just determining if the string is valid English. But how do we tell if a question is intelligent? There are no stupid questions, or so they say, but we think that a good question should have a good answer. So, we run our answering system on our questions to make sure that questions with good answers are rewarded. Finally, after we've scored all of the questions, we choose the best end questions and return them. So what exactly is in this magic answering box? Remember how we turned our articles into bags of weighted stems? Well, we compare an input question with all the sentence bags in the article using cosine similarity NTF-IDF to find the closest matching sentence. The most similar sentence to the question becomes our answer source. For identification questions, we need to narrow down the answer within that sentence. Step 1. Identify the question type. Step 2. Supersense tag all the things. Step 3. Looking only at the words that are not in the question, find words whose sense tags match the question type. Step 4. Return the smallest parsed subtree containing those words. Finally, for yes-no questions, we see if all the important words in the question are also in the answer source. If not, probably something fishy is going on, and we say no. Otherwise, the question seems pretty reasonable, and we say yes.